Thank you. So the last day we have a very less crowd. Yeah. So it is the last day we have very less crowd actually. Yeah. So in your course structure, what is the course structure you are? What are the courses that you have done? I would, yeah, yeah. Mm-hmm. Mm-hmm. Okay. 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 Good. PLC, sir. Okay. Good. Yeah, I think we can start. I think it's 10. We'll start. So today it's a long, I think we'll have a long day. Yeah, so, yeah, good morning everyone. I think in the last class we discussed about the importance of soft sensors, actually predictive models. Where do we need these predictive models? I think I'll just close this part. So, yeah. So where do we need these predictive models and what are the classification of the predictive models we have seen? I think here we can just classify into as a model based as well as the, yeah, mic is not on. It's on actually. Hello. It's on. Hello. Yeah. I think I'll keep it here. Yeah. So we have model based. No, it's not here. And what is the problem with this? It's on. Now? No? It's charged. It's a new one, I guess. Yesterday they kept it. Hello? No, I don't think so. It's okay. Yeah, I can do that. No, I think we can't remove this. Hello? Hello? Yeah, I don't think we are able to hear actually. Yeah. So I think let he come actually. Yeah, he can ask. So, yeah, let's wait for something. Hello? This, I think is hello? Oh, it's not. Hello? Yeah, yeah. That's great. Now my model is learned actually. Next time when I do, I can do it. Yeah. Okay. Yeah. So these are the classification of the different models actually. Kind of one is model based and one is data based. driven, and we have also have a hybrid networks which are integration of this model based and data based. So we will see today in one lecture, we will have a very detailed of hybrid, one structure of the hybrid networks actually, like how do we integrate some process flow information into your machine learning models, so that the machine learning models can be more predictive in nature actually. Okay, so yeah, so let's because the focus is on data driven based networks, so we'll start with the how do you come up with the data driven networks or data based predictive models, or we call soft sensors. So how are you going to come up with these models actually? Yeah, so in order to develop these data-driven models, the first thing is the data collection is a critical part that you encounter. So what do you suggest, like regarding the data collection? So what should it have? Let's suppose I wanted to predict some weather predictions of today. So what kind of data that I need to choose? Whether it should be only 1 month, 2 months, or 10 years or 30 years of data? How does I need to equip my data rich? It's just a more data or something else? Yeah, that is pre-processing, that's okay. But it's just more data points, or it's just less data points with more characteristics? What do you prefer? More data points with less characteristics, or less data points with more characteristics? More characteristics. Okay, so I wanted a data set which has all characteristics. Let's suppose I wanted to read a person's behavior. So I can't just read a person's behavior by one day, right? If he's friend of mine for last 10 years, then I can read him better. I can predict his behavior better when compared to just one day behavior or two days friend actually, because I've seen his different modes of operation or different kinds of behavioral. So the data that you consider actually should have different process conditions, whatever the conditions that you're looking into. Let's suppose you wanted to try to model the vehicle behavior or weather prediction. Actually, it is not just maybe the recent data or 1 month data may not be sufficient. You need to consider the good amount of historical data with good features actually. You need to consider a good amount of, so that the features are present, the characteristics are present, and you can able to capture well, okay? Because you need to, this data, the main drawback of the data driven models is, advantage is easier to develop, yesterday we discussed. The main drawback is extrapolation. If the model comes to see something unknown behavior, it cannot predict actually. It can predict to a certain extent, but not accurately. So as much your features, as much characteristics that your past training data has, the better the model predictions the trained model has. Okay, so that's the first part that you need to look into is the data collection and pre-processing. Once you collect the data and data collection, once you have collected the data, then the next thing that you need to look into is whether the data is nice or not actually. The data is neat, whether the data is neat or not. Actually, somebody was questioning about the pre-processing. Yeah, so here comes the pre-processing part, where you will need to look into whether you have a noisy data, whether you have outlets in the process data, how do you remove these data points, and then you look into whether there are null data points, missing data points are there. It's not that the data completes. Let's suppose a sensor, you are trying to capture the behavior of some temperature in a particular reactor, or temperature sensors are available in particular process actually. So where the temperature was working and immediately there was a shutdown of the temperature, or the sensor was malfunctioning. There is no data coming from the sensor actually. It is zero. So you need to identify those points where the data samples are not available, and you need to remove those data points. This is called data cleaning or data pre-processing, and then get the clean data set in order to build a model actually. Okay. So this is very, very common in the industry. If you just take the data set and I'm going to show you some real industrial data set, then you can see that how the data set looks like actually kind of. You won't get a clean data set unless until you observe the data point and filter and model it. The thing is like garbage in and garbage out, right? If you send a garbage into your machine learning model, it gives garbage out actually. So the good data that you send, you get a better predictions. Okay, so that's the first step. Once you do the data cleaning and data pre-processing, the next step that you look into is a feature selection actually, because you have large number of input variables. Now we are looking more into supervised learning. Okay, we have an input and output. We are interested in how to come up with some predictive model output with a certain number of inputs. So now what are the best features? Yesterday we discussed like if you have 100 inputs, is it good to feed all the 100 inputs to a model and develop a model? It's not, because maintenance cost is higher actually. So I need a lesser number of inputs. Rather than 100 inputs, can I condense it to few inputs, few number of inputs which are having significant effect on the output variable actually. Okay, fine. There you use the feature extraction. I think PCA is already been covered in your course, PCA and correlation analysis. I think you would have learned the correlation analysis part, where you look a correlation between the input and the output data set and find the correlation map, and the one which is having the highest correlation, you select those variables as your input features. Okay, fine. Correlation has been studied. Yeah, it has been taught in the first few lectures. It has been taught, I guess, actually. So you do a correlation analysis and find the input features. That is the one basic approach of doing correlation analysis, where you study the correlation between the input and the output, only the input and output. But there is chance of correlation among the inputs also, right? There can be chance of correlation among the inputs. The inputs also can be linearly correlated or dependent. So in order to avoid those redundancy, the best approach is the PCA. You use principal component analysis, which can produce independent variables. There is no dependency among the variables, which can produce independent variables. That is our next step. First, you can try correlation analysis. If you can get a better model, you can go with it. If not, do a PCA, which can try to come up with an independent set of components, which can be used to as a inputs to your model and develop a predictive model. So once the features are selected, the next is what? You have a data, you did a pre-processing, then you selected some amount of critical features. Yes, now you have input features, and you also know what is the output variable. Next step is, you build a model directly. But there are several models, right? There is a linear model, there is a polynomial model, there is a higher order model, actually the second order polynomial, third order polynomial, nth order polynomial, neural network model, Gaussian process regression model, SVM model. Which one you are going to choose? Is a question. Okay, that's a model structure selection. You are going to select the structure of the model. So which model you are interested to choose? Either you want to start with a linear model, or you want to start with a transformer model, right? There are two extremes. That's a very high complex model and a very simple model. How do you want to start? You want to start with a simple model. Let's suppose you are doing an industrial application. You are trying to aim for an industrial application case study. I don't want a complex model to be implemented in my computer. I want to do a simple model actually. Let's start with a simple regression model and see how the model fitting is working actually. If not, then I'll slowly increase my order of the model actually. Okay, this is more specifically focused on industrial applications. When you go to industrial applications, they want the problem to be solved. It's not what model you are bringing, whether the problem can be solved or not actually. Okay, you can start with a simple model and slowly increase the complexity of the model and see the performance of the model, how it behaves over time. Okay. So that's a model structure selection. Once you select the structure, which kind of model that you are interested to choose, then you estimate the parameters of the model. You need to do a training of the model. You estimate the model parameters or model training parameters by minimizing the error minimization part. Okay, that is optimization. The model tuning or model parameter tuning is that part. So once you develop the parameters are known. Now you wanted to validate on an unseen data set which has not been used, and you test the data set. Okay, so that when your model performance is good, then you can go ahead and implement it in online if it is fine. If the model performance is not so good, then what should we do? Retrain is only one option. Retrain with what? Different types of models. Okay, that is one option. I can go and change the model structure. That is the model structure selection. Initially you selected one structure, that performance is not good. I'll go back and change the model structure selection. And what else other freedoms you have to improve the performance? You can reduce the input features, fine. Or add some more additional input features actually, because the current features are not giving good predictions. Can I add additional features which can be a significant effect on the output actually? I can increase the features of it actually. Okay, so that is one critical thing. I can go back and I can look into feature selection, or I can change the model structure actually. If I don't have additional features, I'll play around these models actually. I'll play around. If I have additional features, I can incorporate few more features and try to again retrain the model. So this process is the one most time. It's not that easy for an actual industrial set or large scale industrial process. When you're looking, it's not that easy. It may take years to fine tune and actually implement a model on real time. Okay, it may take years actually. It's not that easy. Though it's a simple regression model, I will show you that the performance, in order to get a performance, quite good performance, it takes several years actually. So there is a lot of iterative process goes here actually. So okay, you select again, you go back and select the data set also. Okay, it may be because the conditions are changing, you may need a new additional data set, recent data set, again remodel and come back and try to validate. And so once this iterative process, the model performance is satisfied, then you go back into the deployment and monitoring. Finally, we go back and implement it in a real scale actually. Yeah. So these are the different steps of any model. Like let's suppose the machine learning model that you choose, okay, is going to fit here. It can be of any machine learning, right? From the regression model to a higher order large language models or transformer models, any process. But this is a structure that you follow actually. Okay. For developing of any supervised predictive model learning. Okay. Yeah. So yeah, this gives one. Where you wanted to gives a structure of how a soft sensor or model is developed. You have measurements which are coming at a fast rate, that's flow rates, temperatures which are coming, and there are some measurements which are coming at a slow rate. This kind of measurements, like yesterday we discussed one case of health condition where some measurements like temperature can be measured immediately, but there are other conditions. If you want to measure about the process, you need to go do sample, select the report and come. Then only we can able to judge what is the state. So these are like sample data which is coming. So I'm going to, in the case of soft sensors model, I'm going to use both the data which is coming at irregular intervals and regular intervals and come up with a predictive model. Okay. So this is the fusion of it. So let's go step by step what we discussed and look for a simple regression model, and then we move on to slowly increasing the complexity. Slowly we'll start increasing the complexity of it as we start moving on to it. Okay. So we are going to discuss only on the supervised learning part. Right from starting from a regression, we will go into a probabilistic version. We have a regression which is a deterministic. From there, we will move into slowly into probabilistic, and we'll see how the deterministic regression can be solved in a probabilistic way. Okay. So that is very important for the case. You'll see why it is useful to study a probabilistic probabilistic modeling, why it is important. It gives a lot of flavors actually. For the research people who are doing it, you can get a lot of problems. Actually, there are good problems to chunk actually, kind of chunk and eat. Okay. Yeah. So yeah, so I think this graph gives you this is an industrial data set actually, real industrial data set. So when you select a data set of I think the first figure is of an output variable and this is an input variable. This is a raw data which has been taken from the DCS of the industrial system. So when you see, this is the data condition that you get actually. So what you see in the first, is it a clean data? How do you say? How do you say? It varies a lot. You can identify that there are some outliers over here actually, kind of. Okay, and they are significantly for long, means maybe the sensor is gone, it drops down immediately from a 250 to a 50 degrees actually, or whatever the temperature or the flow rate is, 250 to 50. So you can treat this, maybe this is for longer time, maybe because of it's for longer time, it's not a process change, it is not actual normal change, it can be an abnormal change, where there is a sudden drop in your flow rate actually, kind of. Maybe the sensor malfunctioning, sensor is not working and is not giving the result fine. And but there are some other spikes actually. So what about this one? Is it good or bad? Good data or bad data? So see, the most critical thing in the model building is when you get a data, the cleaning part. Whether are you cleaning the right points, or are you cleaning the wrong points actually? What if you clean the right points? Your data is lost. Right, you are missing the data points actually. Okay, so identifying which data point is critical and which data point is not critical, or which data point is outlier, is a challenging thing. It's not that even I can't judge whether this point is a good point or a bad point actually. Okay, so what I can judge is according to I can see that there are multiple changes happening like this. Okay, so there is it's not an outlier. It's not occurring at one instant. It is occurring at multiple instants at frequent intervals. So there is a process change actually. So it's needed, but there are other points you can see that there are some spikes you can see. So you can see these spikes. Okay, this is for a very short time, within 1 or 2 samples the spike is there, and then it get back to the normal point. So these are the outliers. These are the outliers. Okay, so these are like a sensor failed data. These are the outliers, and I think we can show. Yeah, here you can see again there are some data points which immediately suddenly drops within one sample. But if it's for longer time and within a range, feasible range actually. So then you can say that point is a valid point or not a point. So how do you know this all information? whether it's a valid point or not? You have to discuss with the people who are working there actually, in the operators, those who are working in the operator on the field, they know this, whether these data points are all outliers or not actually. So you can't judge on sitting on a computer in one quasi room in an industry. You can't decide that that's a outlier or not actually. You have to go back and discuss whether what is the range of this variable. Let's suppose this variable is some critical variable. What can be this range? If this value can be an outlier considered or a not outlier considered. Okay, that can be sorted out only when you discuss with the operators or process engineers who are working on the field actually. So they give some information that can be integrated here and keep bounds and remove those data points. Okay. So yeah, once you do that, I think here this is more clear actually. Yeah, I think this graph gives like first you select once you get the data set, you do a either before pre-processing or after pre-processing. You can select the data set. It's a 80%, 20%, I think, or 70-30% data set. And generally people try to randomize the data set so that you have the training data has good amount of features or characteristics. You randomize the data set rather than just taking the time series data. You take entire data set and randomize it, and then take the randomized data as a training data and the other some part 20% as a testing data part, rather than just taking a time series data. So that's not a good way of doing it. Okay. So yeah, this graph gives a nice view of several things actually. You can easily see that there are many outliers over here part actually for a longer period of time. Okay. So actually this is a flow sensor. Flow sensor is operating at some particular variable, but you can see there are significant outliers happening, and also sensor failures are happening actually, multiple sensor failures. So if you're just blindly taking this data and trying to fit a model, then it's like you're giving a garbage to your model, and model predicts garbage. The parameter estimates of model are wrong, and the predictions are wrong. Okay, so this has to be taken care. You need to knock out these all outliers actually during the training phase of it. Okay, so otherwise you end up with the problems. So how do you knock out these outliers? What is the best way? That is, you can see visual one way, but what is your your data set is 1 billion points. You can set a range. What is the range? The range is typically of either using a mean, right? Suppose you have a data, you find the mean, and from the mean, how much deviation it is happening. Is the mean is a good way? Let's suppose I'll get answer from you only. This data set is there. Okay. I'll take the mean of the data and then decide plus or minus 3% variation from the mean. Will that be correct? Sorry? Can be correct. If you take the mean, what happens? There are significant outliers, right? If I take the mean will be around the lower value. And if I take a plus or minus 3 sigma, then actually you are knocking out actual data. The mean will be shifted, right? When you have an outliers, the mean will be shifted. You won't get a true mean, the mean will be shifted. So you will get around mean here, and if I just take some plus or minus some percent variation around the mean, I'm actually knocking out the actual data. Because of the outliers, the mean is shifted. Okay. So rather than the mean, generally people tend to use mean and try to knock out the outliers. So eventually you are knocking out actual good data when you try to use a mean. So better to use median actually. Median is the middle part of the data, the center data point. When generally outliers are either the first lowest data points or the highest data points actually. Okay. When you take the mean is sensitive to outliers. When you have outliers, the mean shifts and it is sensitive. So better take the median. From the median, you take plus or minus 3% of the variation. Okay, 3% of the mean from the mean plus or minus 3%, which is less sensitive. Median is less sensitive when compared to the mean actually. So that's what here. When you take the mean, you are getting the bounds as this one. So you are including all the outliers also as your data. When you take the mean, you are including all the outliers in your data. But when you take the median, so you are knocking out, the bounds of the median are very strict. You can see that actually. Okay, the bounds of the median are this one. It's very strict, and these are all considered as outliers. Okay, so this is one point. If you take mean, you will end up in bad results. Okay, so once you do this data cleaning part, the next thing is this is outlier removal. Okay, this is one outlier removal, and there is also something called last time the figure that we saw. There, let's suppose this one. Yeah. So here, I think in two cases you can see. I think here you can see this part and this part. This is a constant value. This is not an outlier. This is not an outlier here. There is no outlier, but this is like a missing data kind of actually. So there you can see that the input sensor is also off. It's giving a constant value, and your output data is also giving a constant value. Okay. So these are all the missing data points. Means you don't have a data point at the time either because of process shutdown, maybe process shutdown for that particular time over a period of time, or the output lab sample is not available actually, kind of. Okay. So this can be of multiple ways you can get the missing data. This or different characteristics of missing data. So you can see that let's suppose you have 5 variables. You have 5 variables and 4 variable sensors are working perfectly, means you're getting samples at every time. And 5th variable stopping, means I'm not getting the data of 5th variable from this point. So you can see from this case, maybe because of this process shutdown or the variable shutdown, you're not getting information from this particular variable. Okay, so this is one nature of missing data where the one variable data is completely missing. The other nature is like you can see that the whole like more than one sensor the data is missing. So this is like a process shutdown. You can say that the process shutdown and you're not getting any data point of it. And you have like multiple sensors missing. This is like a sensor malfunctioning. This sensor is missing the data points here and this sensor is missing the data points here. So these sensors have individual problems and it is resulting in this way. And this is, you can see that what I said, regular sampling. These two variables y1, y2 have continuous measurements, y4, y5 have continuous measurements, but y3 is only regularly is coming. It is only coming at 1 hour, 2 hour, 3 hour measurements actually. In between I am not having. Okay. So these are different nature of the data when you see which kind of what is the nature of the data. So let's suppose, how do you handle this? Is this important? It's very important, right, actually. So let's suppose this is a case. Well, we'll take one case actually, not multiple. Let's suppose this is a case, and this is my output variable, means critical variable, which is only coming at 1 hour, 6 hours, 12 hours, 18 hours. Okay, and you have input variables, y1, y2 inputs are there, and y4, y5, all the inputs are present at every sample, 1 second, every second. But this data is only coming at this point. If I want to fit a model between output and input, what should I do here? What should I do? In this case, I want to fit a model between y3 and y1, y2, y4, y5. Let me see whether I can get an answer. I want to fit a model between, I want to predict y3 hat, which is a function of y1, y2, y4, y5. Is this reasonable? I want to predict y3 by using this data. So first I need to train. First thing is I need to train. So for me, what is the data available? y1, y2 is available. All data points are available. y4, y5 are all data points are available. But y3 is not available, right? If I want to fit a model, you need same data set. What will I do here? Extrapolation. Okay, extrapolation is one way. Either I can say that in between the data points which I don't have, either I use the past value of y3 and keep it constant till I get a new value. And again I keep it constant till I get a new value. Is this correct? Correct? What if in between some changes are happening? I am keeping my quality variable constant. Okay, so if the process is behaving like this, okay, you got a sample here, okay, X sample, but after that suddenly the process changed, okay, and the next sample is coming at here. You don't have any measurement in between this. So now as per that you're saying, keeping mean value, I am keeping it constant till here. Is this correct? You are not able to, you are losing, right? This all information is lost actually, kind of. You are not able to get this part. Average of? Okay, you tell me now. This is one value, this is one value, and again, the next sample is here, and next sample is here. Can I take average? One sample is here, one sample is here, one sample is here, and one sample is here. The 4 samples that is there in that. Now, if I take average, you will be in problem because you will be shifting the actual true value. Okay, you are shifting the actual true value. The best thing is we'll get into that problem how to handle this one. But what is the easiest way is I will remove the data points corresponding to this all. I'll downsample it. I'll only select the data points where actual true lab samples are available. Let's suppose these are the true data points, right? This Y3 is a true data point, and then I select correspondingly the inputs, and corresponding to this I'll select corresponding inputs, and corresponding to this I'll select corresponding. So now the data set is reduced to 4 data points actually. Okay. Generally it's not 4 data points, generally you have a large, like suppose 1 year data set, you will have a good amount of chunk of data set. Okay. So I will downsample. By doing this, what is the advantage? I am not any averaging it. Okay. I am only selecting the true lab sample corresponding to that part, true lab. If I am averaging it, then I am incorporating error in my model training. You agree? If I am keeping an average sample here, let's suppose I average to be a Y3 constant, I don't know what is the behavior here, but I am averaging it out. So I am incorporating some error in the model training itself. So the model performance will be bad. Okay. So rather than that, I will only select the samples at what I see. Only those samples I will select the corresponding input and a corresponding output. This is called downsampling. Okay, we downsample the data. Okay. So actual data points are 3000, but you are selecting only when you are observing the output variable, quality variable. Whenever it is observed, I am only selecting that samples corresponding to that. And I am trying to build a model. So I will come up, initial data set was, let's suppose initial data set was 3000 cross 5. Now when I downsample, the data sets may be 250 cross 5. I may get only 250 data points, but they are very accurate. They are actual true lab samples. I am not incorporating any extrapolation or any other thing. Okay. Only thing is data size is reduced now. Okay. But what you are losing, you are losing some part here because there are cases where inputs are being observed, but the output is not there. You don't have an output data. Okay. We'll see how to estimate that. Generally, you can estimate that. You can actually estimate that thing. So some approaches, what you guys are saying about mean value, extrapolation, these are called imputation methods. We impute the values in between the missing data, but that may result in your performance. You can see when you input the data points in between the missing data, the performance drops actually. Because you are not capturing every data point, right? So this data point you are saying keeping an average. So you are getting your data point here and here, then you are keeping an average here. And again after this one, you are getting a data point here and you are again keeping an average. Right? You are using this sample and keeping an average for this actually. Okay. So if the sample size is lesser, I agree with it. If the sample size is like 5 minutes, data sample is coming. It's okay. I can average. Okay. But in chemical process, it is, or any other pharmaceutical process, it is 6 hours. You get sample every 6 hours, 6 hours, 6 hours, 6 hours, 12 hours is there. So if I average, I'm approximating badly actually kind of. Okay. So that's not a good way. So one can estimate it by using entire data, one can estimate it. We'll see that how it is. That can be done only through probabilistic way. So in a regression, we can only do this one. Either impute the data, okay, add average data or keep the data, past data constant. That is what you can do using deterministic approaches. But using stochastic approach or probabilistic approaches, you can actually estimate entire vector actually. You can estimate the entire vector. Okay. Yeah. Is clear? Yeah, these are different nature of it. So once you do this missing data problem addressed by using averaging or something, then you have a reduced data set, which is a clean data. You have removed the outliers by looking at the median You use the median, you remove the outliers, and then you also used missing data problem by either downsampling the data or by using the imputation method, any of the imputation method. And then we get into feature selection. Pre-processing is done. You have done the pre-processing, then gets to the feature selection. In the feature selection, you have X number of input variables, but I don't want to use all the X number of input variables. I wanted to select which are having a good correlation with the output variable. Right? That's a way. It's a supervised learning. So I will only select the feature inputs which are having a good correlation with the output actually. So I find a correlation matrix. So the correlation matrix is nothing but the normalized version of covariance matrix. You know covariance matrix, right? Variance is the diagonal elements and the off diagonal elements are the cross covariance matrix. So if you now normalize the covariance matrix, you get a correlation matrix actually. So in order to, the normalization is done only because in order to get a metric, a scalar value, okay. So when you do this, when you find given a data set, this is the input data. This includes all the data, entire data set, which is first 8 rows corresponds to input, and the last row corresponds to your output data. Okay, you have inputs and your output. Now this is a data matrix D. I want to find a correlation between among every variable. Actually, I'll find a correlation coefficient values actually between each variable to U1 to U12 and input to every input to other inputs as well as every input to your output variable. Okay. The most interesting for me important thing is how input is correlated with respect to output, because I wanted to select features which are having significant effect on output. Okay. So this correlation value generally ranges between -1 to 1. So if the value is close to 1, it is good. The value is close to 0, the correlation matrix is poor actually kind of. So you need to select the variables which are good, close to 1 actually kind of, yeah. So I think in the case of Python, you have this heat map. I'll show that where you input the data matrix, give the data matrix, find out, it will find the correlation matrix structure actually, and select the variables which are of correlation between -1 to 1. Okay. So once you do the correlation variables actually, once you select the correlation values, so the next thing is you selected the features. You did the cleaning, you have selected the features. The next step that you are going to do is model structure selection. I have the input variables are available. I've selected the models input information. Now the next thing I wanted to go is whether which kind of model I want to fit now for this particular process. Okay. So I can start with the simplest model is a linear regression model. I'll start with a simple linear regression model. Especially it's not for research, but it's for industrial applications. When you're looking at industrial application part, the best thing is start with a simple linear regression model and see whether you're able to fit a model between the input features and the output. And then slowly start changing the models right from the regression to polynomial regression and using ARX model or auto-regressive models. Have we discussed about auto-regressive models? No? Yeah? So I'll just give these are powerful models actually. Auto-regressive models are generally because nowadays when you see in transformers, when you study transformers and dissect and go inside, the inside that is sitting is auto-regressive. They are auto-regressive in nature kind of actually. Okay. I'll just give an example of an auto-regressive model. Then when you do your projects, in your individual projects, you can get a feel of, you can try to implement it actually. You should know about this part. Yeah. Yeah, see, correlation matrix is among, it's a linear mapping, linear correlation you are trying to find. Okay, so correlation between input and output and the correlation between one variable to other variable. But there can be multiple correlation among the variables also, So the PCA, this correlation analysis doesn't do that. It only finds a correlation between input and output, one variable to another variable. But when you use PCA decorrelates this entire correlation matrix. It can also give an independent variables which are not correlated with any other variable actually. Okay, so that PCA has much higher advantage. Okay, but in the PCA you lose the features. when the components that you're going to get, it may be a combination of multiple variables. It is the principal component that you're going to get after feature selection. It is not one variable, it may be a combination of multiple variables. Okay. Yeah. You understood the difference? Got it? Yeah. The correlation analysis doesn't find among multiple variables the analysis, but the PCA gives a correlation matrix. One means the PCA gives the variables which are independent of complete each other, among the inputs also actually. Kind of. Okay. Yeah. So the best way to start is use a simple correlation analysis and see whether you are able to get it. But yeah, and also it will dimensionality, means it will give independent features which are a combination of variables. But in the correlation analysis, you will never get a combination of variables. It's are individual variables actually. Yeah. Yes, let's suppose there are two variables, two inputs, which are identically affecting your output. So do we need those two inputs? Do we need two? Because they are individual, identically. I don't need actually. I need to. They are redundant sensors are. It's like redundant sensors. I only select one variable. Why I need to select two variables actually? So in that way, PCA helps you actually kind of to coming up with a joint combination of variables actually, not one variable actually. Yeah, means correlation among the inputs is important, or understanding of important, so that you reduce the number of variables significantly. There can be a lot of redundant variables which are not required actually to monitor or to maintain those. So you can actually reduce those by doing this analysis. Okay. So yeah, I think I'll just touch upon the auto regression ARX based models. So I think especially autoregressive exogenous models we call actually. So what is your regression problem? General linear model yk, let's suppose yk equals to a into, this is my input 1 u1k plus b into input u2k plus some c into, let's suppose you have three inputs and you are considering this linear model, fine? It is a linear model. So what does this model gives information? When you look at the model, the input u1 is affecting the input u1 at the kth sample is affecting your output y at the kth sample. At the current kth sample is affecting output at the current kth sample only actually. Okay. The same way this one u2k is also affecting output k and u3k is also affecting output k. But let's take example of your day temperature. If you're just monitoring your day temperature over a day, okay, that's your output variable, okay, yk. So you wanted to predict the day temperature in a Nagpur region or wherever, which region actually, or VN80, around VN80 you want to predict. So is it only yk is depending only on external parameters, or if I know that entire time series data, let's suppose if I know this data and I say that now yk is not only dependent on external factors like a wind or other conditions, it is also depending upon its own past temperature, its own past value, its own past recent value. You agree? It's a time series data. Weather conditions are time series data. It slowly changes with respect to time, right? So when I want to predict the temperature at 10:40 today, if I take a recent sample which is available 5 minutes back, will that be helpful for me to predict current sample? Right? It can be helpful, right? So now I'll say that I don't want this linear regression model. Now I know that this is a time series data. Now I wanted to change my model into a into yk minus 1. The yk is depending on its past value, the immediate past value, or it may be depending on the past 5th sample, or it may be depending on past 10th sample. Let's suppose you are doing a seasonal predictions, okay? Okay, so I wanted to predict at this region. I think you will only come up with autoregressive model now. Okay, so let's suppose this is yk and this is k minus 6 months, k minus 12 months, and k minus 18 months. So what can be your input features? This is my output I want to predict. What can be your input features now? Huh? Past data is your features, okay. But by looking at what you can say exactly, what can be the feature? Input feature can be. Huh? 6 months back. I don't need to consider all this data, right? If I want to predict at this region, I want to predict only these peaks. Let's suppose every peak I want to predict. Why I need to consider all this information? I will say that now I'll come up with a model of yk is depending upon yk minus 6 plus yk minus 8 or 12 plus yk minus this one. So alpha into, a into b into c. A simple linear model. It is autoregressive in nature. Yes, that is also a good one actually. So yeah, that's good. That's good. I can only take yk minus 6 because yk minus 6 information is already this is already affected by this way. So I can only collect this information. Okay. Okay. So that you will connect it actually when you discuss later. This is called a Bayesian network. One way of reducing further features. So if this I am able to come up with this result itself, I'll select only this feature. Okay. So in a simple regression model, you are only considering the current input with the past input. Okay. The current sampling time actually. So current input UK at this time affects this part. So you are not looking any past information in your data or incorporating any past information in your data, time series data. So but autoregressive models are like you have a measurement, the current measurement not only depends on the inputs, it also depends on, it doesn't depend, it not only depends on your inputs U1, K, so on, it also depends on your past own measurement values. It has its own past measurement values. Okay. So there will be a lot of difference when you try to model this one and this one, the performance you can see a significant improvement actually. Okay, because this is a time series data, this has a good correlation with its own recent data point. Fine? So out, yeah. You are not improving the data size, you are actually incorporating more features, you can say. It is like additional, initially for this part, what was your data? Your input U and your Y. What are your input features? You only input U1, U2 and U3 and output was Y, right? This was the thing. Now for this model, what is your features now? Entire data set will be, what is your input and what is your output for this model? What will be? So yeah, I also have a measurement which is one time delay. Okay, yk minus 1, yk minus 6 and yk minus 8 or 12 and you have uk1, u1, u2 and u3 are the inputs. You have inputs and you also have measurements which are 6 months delay samples. Okay, or 1 month or 5 minutes or 10 minutes, whatever it is. You're using past time data, immediate past data. Fine? These are completely different models. They are not same. So the performance of these models will be much higher when compared to just a static regression. These are a static regression, simple linear regression model. But these are auto-regressive models. You are trying to incorporate some additional features which are having a correlation with its own past value. Okay. Especially in your seasonal, you can collect actually. So if I want to predict at this peak, and I'm no need to worry about this one. If I can incorporate these as additional features, I can get much better predictions rather than just some independent variables, some other inputs, right? What is right? It's an auto-regressive model. So I think you would have studied about neural networks, right? Neural networks is you can make neural networks as auto-regressive. Any machine learning model can be made as an auto-regressive model. Okay, by changing your input data set. If you can incorporate your input data as additional features, you can modify your actual model into an auto-regressive based model actually. Okay, which are powerful models which are widely used in automotive industry actually, kind of in chemical industry we use auto-regressive models which are powerful. So you can first try a static regression model like a static neural network and then change your data set into this one and see the performance, you will eventually see that the performance can significantly improve it actually. Okay, so that is being observed. Okay, so all the models like LSTMs or neural networks, whatever the you see what deep learning networks are static networks actually. Okay, they are not auto-regressive in nature. You can modify them into an auto-regressive nature by modifying your data set, what inputs you are giving it to it. Fine? Yeah. So this is, I think why I went into this one, because it is important to know this, because it's not just you take a data and fit some regression model available in the tool. You can actually tweak your model to get a better performance by just adding few more additional layers to your input data and adding the features corresponding to it. You can get a better performance actually. Yeah. Okay. Yeah. So, yeah. Yeah, here you can play with the models, which model you wanted to choose, step-by-step selection of the models from linear regression to a higher order model. So once you choose a model fitting, then what? What are you going to solve in the regression? How do you train? Yes, you have selected some part of data. So you wanted to fit a model. So what are you going to solve? You estimate the parameters. How do you estimate the parameters? Okay, you split the data. How do you then? Sorry? Yeah, use the least squares method and to estimate the data, right? So you have the model that is being, let's suppose you are fitting this model, okay? So you have this model which is a y equals to a into uk plus epsilon. Let's suppose it's a simple linear model, okay? And now you have a data, the data yk data is given. Yk1 to Yn data points are given. So I wanted to make sure that I wanted to minimize this error as close to as 0. If this error is close to 0, then this can be my model which can predict my true measurement actually. Okay. So I wanted to reduce the error between the yk, which is y planned data, and y predictions. Y predictions are nothing but the model a into un, which is nothing but y planned minus y hat is nothing but a into un. So this error I wanted to minimize it for a batch of data. Okay. So I can do sum of square of errors is one approach, or sum of errors. Can I do sum of errors? Why only square? I will do sum of errors. Minimization of sum of errors. What is the problem? Can I do? Yeah, I wanted to minimize this error, right? I have n data points. I wanted to minimize sum of I equals to 1 to n, whether it should be square of errors or just a sum of error. Sum of error. What happens if it is sum of errors? Is it correct? Error can be positive or negative. Okay. You wanted to minimize, you wanted to make this error to be 0, right? By solving with respect to theta, you wanted to select theta, that is a, the parameter a, optimal parameter, so that this error is 0. If I am just doing a sum of errors, there is a chance that the error can be positive or negative, and the error can be 0. Without minimization, you are solving the problem, the error is becoming 0 actually. So the theta is suboptimal. You are not solving the problem at all actually, right? So that's why you use square of errors, or you use mod of error, mod of sum of mod of errors actually, absolute errors, okay? So that you avoid that cancellation among the errors, right? Error gets cancelled, error can be positive or negative, it gets cancelled. So you try to solve this minimization error problem and you get the parameters theta hat, okay? That's what you do in the case of regression, that's the least squares, you try to solve the sum of errors. So this, if it's a simple linear regression case of, you can use first order optimality. I think it has been taught to you, I guess. You use first order optimality condition, means gradient. When this becomes minimal, or when this objective function error becomes 0, or the minimal. When the gradient becomes 0. When the gradient becomes 0, the objective function of that particular error is 0. So let's suppose this is the objective function that you're solving, which is nothing but sum of I equals to 1 to n error square. So the objective, as you vary theta, the objective function varies like this. Okay. So at one point, it doesn't vary at all actually. Okay, and start increasing that part. What is this point? What is happening here? Here at this point, the difference dou j by dou t is 0. Okay, there is no gradient change is happening. Okay, so that is called first order optimality. So where the function is not varying actually. So it means if the function is not varying means you have reached your minima or maxima. Okay, minima or maxima. You have reached your minima or maxima when the function is not varying actually. You have reached the local hit. Either it can be minima or maxima. To decide whether it's a minima or maxima, you do a Hessian. Do a second derivative, then you will get to know whether it's the second derivative is increasing or second derivative is decreasing actually kind of. Okay, if it is increasing, it's a minima. If it is decreasing, it's a maxima point actually, right? Yeah. So you can get an analytical solution. I think the analytical solution I saw in the board when Professor Bhushan was teaching. Analytical solution you can get by just differentiating with respect to theta and equating it to 0. You will get theta hat equals to some parameter, x transpose x inverse x transpose y kind of. Okay. So yeah, so this is one, the same thing you can do it for the case of if your model is auto-regressive model, do the same thing. The model just changes your model will be of a into yk minus 1 plus b into past how many features you are considering, yk minus 2, c into yk minus 3, uk, u1 plus u2 plus u. These are inputs and these are past outputs and inputs. So use the same model and do the parameter estimation. It's the same process. They're like how you do for the simple regression problem. You're going to do the same process, but you are getting additional features as its own past values of your input. Okay, is clear? So this is basic structure of any predictive model development where you start from pre-processing. You start from data pre-processing. Then you decide structure, what structure of the model that you wanted to choose. Then you get into the modeling assumptions, okay, and the parameter training. And then online, once you do the parameter training or the training data, you get into online data, unseen data, completely unseen data, okay, and predict on that particular unseen data. And once this is, as I mentioned, it's keep on iterative process. You keep correcting this model, okay, until unless it is properly satisfied and implemented in the DCS, okay. So what if you develop a model and you implement it? Will it work for a lifetime? Okay, it doesn't work for a lifetime, right? Actually, so let's suppose I have taken a medicine today. I got I'm happy. Means I monitored my health and I was able to predict what my conditions are, and accordingly I got an action. So now the system is in place. And again there will be some trouble, right? There should be some maintenance. I need some feedback from the doctor again, actually, right? So predictive models are also like that. So it's not once a model is developed, it's not universal model. The conditions change, the process conditions change, environmental conditions, whatever the process that you're dealing with, disturbances keep coming, unmeasured variations keep coming. So you need to maintain your model. Model maintenance is critical in real time actually. Okay, it's not just once you develop a predictive model and leave it, it's not the business. You need to keep updating the model because conditions are changing. When the conditions are changing means the new behavior is happening actually in the process. The model has been trained on a different behavior. So the model has to be again retuned or re-evaluated actually, kind of re-identified. You can call it a re-identified. So here is, there are multiple strategies of model prediction where you have a soft sensor, it's predicting. So you take the predictions, means you take the prediction value and you also get this, we told that the critical variable is available at every 6 hours, right? You take the sample, you take the error between the prediction and your lab sample and you see that whether error is growing or error is 0. If the error is growing, means model is performing poor. Model is not performing poor. Okay, model is performing poor. Then you need to make some corrections actually. Either you add some bias maintenance kind of. There are some issues underneath. To update, it's called updation of the model. We are trying to update the model. Either you re-identify the model completely, take a recent data and re-identify the model. That is one approach. Okay, means turn it off the model soft sensor which is there. Again, take the recent historical data, update the parameters. That is one approach. The other approach is, can you online do it? Okay, can you online do it? One simple way of doing it is, I'll give a structure. See, these are all industrial, when you go to your internships or industry projects you're handling, these are very critical actually, because you develop a model and you leave, right? Then who is going to take care of that model? You develop a model, keep it and give it and leave it actually. Okay, you have implemented it online, but who is going to take care of that model over a period of time? So it should be automatically taken care, right? Actually, you need something. So let's suppose, I'll just tell someone very basic case of model maintenance. How do you do it? So you have, let's suppose a reactor or any particular process that you're dealing with it. You have a reactor or you have anything. You have certain inputs. Don't think that it's a chemical, it's any process, any dynamical process. You call it any dynamical process. Okay, so you have an input, U1, U2, U3 are there actually. And you have developed your predictive model, that is a soft sensor or predictive model. You developed, okay. So now your measurements are coming at, the quality measurements are coming at 6 hours, 6 hours, 6 hours, okay. Every 6 hours you are getting one sample, right? You are getting one sample here, one sample here, one sample here, okay. Every 6 hours you are getting one sample. So I say that this is 6 hour sample, 6 hours measurement. Why measurement is coming at 6 hours, okay. Now I am sending this input to my company. This is where are you putting this soft sensor? In your PC, okay, in your computer, in the controller. Controller is nothing but digital computer, actually. Okay, in your personal computer or whatever when you go to industry, there will be a control room, kind of digital control room where you have a PC. So you send this inputs to your PC, okay, and you're getting the Y predictions, okay. Okay, so this is open loop. I'm not using any data here. This data is coming, predictions are coming, and these are coming at real time. Okay, but I want to check whether these predictions are correct or not. I need to do that, right? Or shall I leave it like that? Assuming that this is correct. Okay, for one day it's fine. You keep it one day is fine, and some other conditions, some operator comes and change some input conditions, then the model may go in a different direction, right? I need to monitor this. So what I will do is, okay, this is real-time prediction and this is coming at every 6 hours, right? So I will take the plus and minus error. Okay, I'll take the error between the difference. It's just a very simple approach. It's not any math or much is involved. There are other approaches you can do it. I'll take the error. I got error, right? When you take the difference between this one and this one, I got error. Now, if I'll add this error to my model predictions. Is it correct? If this error is 0, there is no correction here. If this error is not 0, then there is some chance of correction is happening actually. You agree? But this one question is, you are getting only this sample is 6 hours, not every time. So you can't correct this model and every time you can't correct it, right? The error that you get is only every 6 hours, not every second. You get only one error every 6 hours. So I am taking that error and adding it to my model predictions. Okay. So to correct my model predictions. Okay. So this is one simple way of doing. Let's suppose your model is y hat equals to ax plus bu is your model. I am adding some error term to it. This error is the difference between your model predictions, past model predictions, and the current. Actually, kind of. I'm giving some weightage to the current measurement and some weightage to the past measurement actually. Okay. This is a simple way of sensor maintenance, soft sensor maintenance. I'm just adding some error part and doing it. If this is not working, the other way is stop this. Okay. Don't send to it because it's already performing bad. Again, take the data and re-identify the model. That is another way. The third option is online training actually. Okay, you're trying to adapt your model online actually. You take a recent data and again do the all analysis of model parameter training, but taking recent window data. It's like window based training. You take a recent historical data and keep moving it actually kind of. Okay, so it's called online training of your model. Okay, so this is called model adaptation or model maintenance, which is very critical in the process industry. It's not just you develop a model and put it, it doesn't work. Okay, it will fail within a week, or a week the performance will go bad. Again, you need to do these error corrections actually to your model, or adaptation of the model has to be done. Okay, it's a long-term process, it's not a small term. Yeah. Okay. So let's look at one case study which before we're getting into the next part. So we want to take a break. When did we started? 10. We have 15 minutes actually. Yeah, 11:15, right? Yeah. Yeah. Let's take one case study before getting into the next part of it. I want to discuss the industrial case study. It's a simple regression model. I have not used anything. It's because this. I think mostly this session is whole sessions I am planning to highlight the industrial relevant applications, more of industrial relevant applications. Okay, so some students who are doing PhDs, they can take it as a project, research project also. The students who are doing interns actually, you can look into these domains. These are domains where you can actually go and implement and make some difference. Okay, so let's suppose this is one industrial process which we have in oil sands industry. We have this oil sands industry in northern Canada. So this is where you have a crude. Okay, in refineries, what you do? You get a crude. You get a crude from Ukraine, Russia, Iran, Iraq, and then you get into our refineries. Then we do pre-processing of the crude, and you get a actual the components. But in Canadian oil industry, the crude is nothing but the sand, oil sand. In the sand, they have a bitumen. Okay, they have a sand. They extract this oil sand and do some processing. So this is one kind of process actually. So those are chemical engineers, they can relate it actually kind of much well. Okay, so this is one kind of process where you send the feed, where they send the crude into different, it undergoes through a different process, chemical process actually, and you get a final product desired. It may be kerosene or gasoline or diesel, petrol, whatever you are doing is you can get a different. So in all this, there is one thing which is emitting is the sulfur. Sulfur dioxide is emitting into the atmosphere. Okay. So the critical component, as I was mentioning in the last class, they want to monitor the sulfur emissions into the atmosphere. The sulfur emissions cannot be more than certain ppm levels. They want to monitor it actually. So further, they want to develop a predictive model. Okay, because they have a equipment, but they have one equipment of analyzer, but these are several units are there, several plants are there, not one plant. There are several plants. One analyzer cost was around 5 to 6 crores or 10 crores actually. Okay, they don't want to use multiple analyzers at multiple places. Want to cut down the cost of analyzers or hardware equipment. Okay, so what is the remedy is a soft sensor. Okay, so this seems very simple process, but it has many variables, around maybe 100 or 250 variables were there. Then we did a lot of correlation analysis, PCA, and we were able to come up with the features. Very simple, around 7 to 8 features have come out. Okay, 6 to 7 features have come out. So once you select the features, and this is my output, and these are my input variables. Okay. So what is the next part is data cleaning, data processing, everything is done. Then model structure selection. Which model I want to choose? The choice of the industry was to select the simplest model because we want to implement and we want to maintain it for a longer time. So come up with a very simple model which can implement it in real time. Okay. So we have chosen a simple regression model of around, I think here it is 15 inputs. I think it's 7. I think it's wrong here. 7 inputs. So this is the performance of the model actually that we have implemented. It's implemented in real-time process industry. Okay, in a large-scale real-time process industry. So what you see is the blue points. You can see, I think if you cannot see the timings here. If you can see the timings here, it is coming every day 12 a.m. one sample. So the blue dot corresponds to the lab samples, the analysis of the report. Okay, one particular sample, it is coming only at every 12 hours, 12 hours, 12 hours. Okay, it's not coming regularly, it's coming at every 12 hours. Okay, so and the pink one corresponds to my model predictions. These are my model predictions, and these are the true value. Okay, so but are this model correction? Are this convincing for you? Huh? Means you are saying there is a difference here. Okay, so okay, so we'll come to that. What about that one? That is matching. This is not matching. So you should ask what is the difference between these two. Can somebody say, can guess what I am doing that case and what I am doing this case? By looking at the results. By how do you shift it? Huh? I added bias actually. I just added bias. Okay. So this is without bias. Without any bias, I developed a model. So I don't want to correct the model initially. Okay. I just took the training and testing data and I tested the data. So then I'm checking whether what is important here in this when I'm doing it. I wanted to see the trend of the data. The data trend is critical for me actually. Let's suppose the ppm level is increasing. Okay. Then my model prediction should not go negative direction. What happens when the model predictions go negative direction? Actual ppm is increasing in the process in the outside, but my model is predicting negative. And these blue samples are available only at every 1 day. What is the problem here? If my, let's suppose this peak point is going in a different direction. Huh?
I will be fine.
You will be
Fine heavily.
You'll be fined heavily actually, that's right, because your model is predicting wrong actually, right? The direction is going wrong actually. Though it's a bias, I'm not worried about the bias at all. I'm interested in the direction actually, more in the direction part, which direction it is going. If it is, let's suppose if it is very close here and it is going in a negative direction, it indicates in that there are lesser amount of ppm levels, but actually the process is emitting higher ppm levels. The direction of the variable is critical for me. So I'm only looking, in the first case, I'm only looking at the direction part. Once this direction is fixed, I'm correcting the model. I'm just adding the error and matching the model part. Okay. Initially itself, if I start adding the error, means you are losing that whether the direction is correcting or not. You should not do that. Correction has to not to be done at the test. When you do testing, it should be without any correction. It should be just predict the model. Once you start predicting, once the direction, everything is matching, then you start modifying your model by adding the additional bias term. Okay. Or else you are trying to rectify your mistakes starting only by adding the error term, by using the real information and adding the error term. That's not correct way. Okay. You tell me. You're a process engineer. It's very tough to decide that's an outlier or not actually. It's very tough, I can't decide. Only the thing that you can decide is because the sample is coming only once in a while. Only thing is you can go and discuss with the engineers at that time what happened to the process. Is there any abnormality in the process? Because if there is, see all the region was around here and in between the last 2 days, there's a shoot of sulfur ppm actually. Whether any process changes are happening actually. And this is, means detecting, saying that this is an outlier or not can only be decided by the discussion with the engineer actually. Means you need some information from them who are actually working on the field to get that information. Or else you can't decide that's an outlier or not actually. It's difficult. Means that is very critical. That's what outlier, you have to really discuss with them. You can't delete the points. Tools, no. See, if you just here, if you use machine learning algorithm, there is a chance that can be out actually. That what if that is because I was involved in solving the problem. The manager was involved in catching that peak. You predict that peak, I am fine with it. I will give you a job kind of. He was like that. You predict the peak. That is. But for us, when you see as a machine learning, we see that that's an outlier actually. But for them, it is the most important thing because that is abnormality. If let's suppose in that case, I don't have analyzer and my model is predicting it, that's BPM is increasing, then I can take a decision making immediately. I can inform my operators or make corresponding decisions immediately. I can do it. Okay. So that is more important for them. This process they are not worried because this is normal operation. Even if my soft sensor is not performing or if I'm not getting reading, it's fine because the process is normal. But this is abnormal actually. So I want to catch the abnormal peak. Okay. Yeah. So you need to do a lot of analysis to decide whether it's an outlier or not. You need to go back and look like corresponding this, right? You should correspondingly look to your inputs. Input is affecting your output, right? if the inputs are all in a normal operation, then there can't be an outlier in the output until unless the lab analysis was done wrong. Somebody has made some gadbad in the lab analysis. If there is an input fluctuation or input like as we saw the previous graphs, where was it? If let's suppose here, you can see here the input was off, the sensor was off, and the corresponding output is this one. So by this you can say that this is an outlier actually. Yeah, this is an outlier, right? This is an outlier because the input also is off, the output is off, it's an outlier. But if the input is in a proper operating mode and the output is functioning badly, then you can say that there is something problem actually. Yeah. So yeah, deciding that is. I don't think you directly use outliers in the machine. It can create chaos actually kind of. Yeah, better not to use direct tools actually kind of. Better first visualize and then you decide which parameters to between and select the ranges of the variables which need to be considered as an outlier and not that are very critical points. Or else you keep losing the data points and you start predicting, you can't predict actually. Yeah, those points. Okay. So yeah, this gives one example of a simple regression model which has been implemented in industry. When you go back to any process industry, you can try with simple models, then start building the higher order models. Okay. So I think next part will take 5 minutes break. You want to take a break? Because 11:15 I think we have a break, I guess, right? Yeah, you can take some break, and then we'll start the second part of it. Yeah. Maybe 11:30 we can meet. Yeah, 11:40, 11:30, 11:30 we can meet. Yeah, I can explain.